Hello, everyone. Welcome to this talk. My name is Tselil Schramm, and I'll be presenting on how subexponential linear programs can approximate max cut. This is based on joint work with Sam Hopkins and Luca Trevisan. Okay, so let's get started. So the topic of today's talk is combinatorial optimization, in which we want to optimize over some discrete set. So one canonical example is the max cut problem. In max cut, I'm given as input a graph G with n vertices and m edges, and my goal is to output a number, which is the maximum fraction of edges cut by any partition of the vertices of the graph. So for example, if we look at this graph here on the bottom left-hand side, our goal will be to assign to every vertex a label, either +1 or -1, such that the maximum number of edges receive different labels on their endpoints. So for example, here in this graph, this is the maximum cut. Okay, and we can represent the maximum cut value with the following integer program in which I have n variables, one for each vertex, taking values either + or -1. And this polynomial encodes the fraction of edges cut by an assignment of the variables. Okay, but computing maximum cut is NP hard. So instead, we turn to the question of approximating the maximum cut value. And the tools that we often use for such combinatorial approximation problems are linear and semidefinite programs. So linear and semidefinite programs are tools that apply in the following very general setting. You want to optimize, let's say, a linear function over a complicated set. And the set might be complicated because it's non-convex or because its description is very large. As is, for example, the case when we want to optimize over sines, like in the max cut problem. And the strategy is to take some convex relaxation of a set S. So that is, we take some set S prime, which contains the set S as a subset. It's possibly a higher dimensional set, and then we perform optimization over S prime instead of over S. Okay, so relaxation naturally yields approximation because since the value, since S is contained within S prime, naturally the value over S prime will be larger. So this gives us a way to certify an upper bound on the value of the optimization problem. And furthermore, we can often approximate solutions via rounding algorithms. So what you can do is you can take the point that is the optimum in S prime and project it somehow into S to get an approximate solution of comparable value. And two of the popular nice sets that people use are linear programs in which you are maximizing a linear function subject to linear constraints, and also the constraint that your variable lie in the positive orthant. And in semidefinite programming, the setup is almost entirely the same, except that instead of the positive orthant, you now get to have x lie in our m for m n by n. So we can think also of x as a n by n matrix. And then we require that this matrix lies in the positive semidefinite cone, meaning that none of its eigenvalues are negative. Okay, and in general, our goal will be to understand the approximation quality as a function of the relaxation size, because the relaxation size corresponds to the amount of time that we must use in order to solve the relaxation. There's also an analog in proof complexity. So linear programs correspond to cutting planes proofs, and semidefinite programs correspond to positive Selinsess proofs. So alternatively, the goal is to understand the approximation quality as a function of the proof complexity. And in general, we know a dramatic separation between linear and semidefinite programs. So Braun, Fiorina, Pokuda, and Sawyer show that there's a polynomial-sized semidefinite programming optimization problem, so that any constant factor approximation requires a linear program of size exponential in n. Okay, so this is a very dramatic separation between linear program and semidefinite programming. And today we're interested in the following question. Is there a similar dramatic separation for max cut between linear programming and semidefinite programming, and also for other combinatorial optimization problems? Okay, so zooming in on max cut a little bit more. So first, it's very easy to get a half approximation for this problem. What you just do is you output a random cut. Okay, so if you look at a random cut, meaning you assign every vertex the label plus or minus 1 equally with probability half, it's not hard to show that any edge is cut with probability 1/2. And therefore, you can get a cut of value half in expectation, and it's not difficult to de-randomize this as well. So that's just setting the baseline. From now on in the talk, I'll say that a trivial cut is a cut of value half, and the goal will be to see whether we can beat this trivial half approximation. So in 1993, Delorme and Polyak introduced the basic semi-definite programming relaxation. So that is, you start with the integer program that I showed several slides ago. You take a very natural semi-definite programming relaxation of it, and you end up with a polynomial size semi-definite program. And then in 1995, Gomans and Williamson showed that this semi-definite program gets an approximation ratio 0.878. So much better than the trivial approximation. And this result came out, it was a big surprise. And in the early 2000s, work of Coate, Kindler, Mosel, O'Donnell, and Mosel, O'Donnell, and Miliszkiewicz proved that it's unique games harder to get a better approximation ratio than that achieved by the Gomans-Williamson relaxation. So assuming the unique games conjecture, 0.878 is the best that we can do in polynomial time. But meanwhile, linear programs seem to be stuck at half approximation. So it seems like they can't do better than trivial. So this theorem is the culmination of many other theorems. I'll go into a little bit more detail about the literature somewhat later in the talk. But essentially, the bottom line is that combining results of Charikar, Makarichev, and Kothari, Mecca, and Raghavendra, no linear program of size less than subexponential can do better than half plus epsilon. So what this means is that it seems like subexponential LPs cannot approximate better than trivially. Okay, here I'm okay. There's like some fine print, which is that this only applies to linear programs whose constraints don't depend on the input graph itself. All right, but then what we are able to show is a converse to this result. So what we show is that for each delta greater than 0, the degree n to the delta Shirali-Adams LP, that means some linear program of size 2 to the n to the delta, can get a approximation ratio of half plus epsilon for some fixed epsilon greater than 0, not depending on n. So what this shows is that subexponential linear programs actually do provide non-trivial approximation to maximum cut. Now, okay, this approximation is not it's non-trivial. It's not that good. Here epsilon is going to be exponential in polynomial in 1 over delta. Okay, so it's not like we're claiming that LPs can match the performance of semi-definite programs. But still, the separation that we see between linear programs and semi-definite programs is not as dramatic in the case of max cut as it is for arbitrary optimization problems. Furthermore, we show that polynomial size linear programs, so that means polynomial time LPs, can approximate max cut in a large class of graphs of bounded threshold rank. What does bounded threshold rank mean? So the tau threshold rank of a graph is the number of eigenvalues of the graph's random walk transition matrix, which are larger than the value tau. Okay, so graphs of bounded threshold rank, you can think of them as either random graphs or very good expanders, or the union of several, constantly many, constantly many expanders. So what we show is that for such graphs, a polynomial size Shirali-Adams linear program, so a polynomial size linear program obtains a approximation of value close to 1 for maximum cut. Okay, so even polynomial size LPs can give non-trivial approximations to max cut in a large class of graphs, which capture, for example, random graphs. We're also able to show that this phenomenon extends to additional discrete optimization problems. For example, in unique games, we show that subexponential sized linear programs can obtain approximations that distinguish instances of value 1 minus epsilon from instances of value less than epsilon. So this is qualitatively similar to the best semi-definite programming-based algorithms for unique games. And we can also get similar results for many other 2CSPs. Okay, so the bottom line is that for many combinatorial optimization problems, LPs can give non-trivial approximations. Okay, so what I'm going to do for the remainder of the talk is I'm going to give you a little bit of a more zoomed in view of the history. So fill in the details of the history a little bit more, and then I'll give a little bit of a taste of the proof. Okay, so for the history part. So as I already mentioned, in 1995, Gomez and Williamson showed that the basic semi-definite program, a polynomial size semi-definite program, gets approximation ratio 0.878. So much better than half for max cut. In parallel to this, we have seen lower bounds against linear programming hierarchies. So what are linear programming hierarchies? They're essentially structured families of linear programs where you can increase the size of linear program to obtain better and better approximations. So a little bit more on that later. But in 2006, Schoenebeck, Tulsiani, and Trevisan showed that in the Lovász-Shriver linear programming hierarchy, you need exponential size linear programs in order to approximate max cut non-trivially. And in 2007, De La Vega and Mathieu showed that in the Shirali-Adams hierarchy, so Shirali-Adams is a stronger hierarchy than Lovász-Shriver, polynomial size linear programs can't get approximation better than 0.51. Okay, so what are Shirali-Adams LPs? Well, what Shirali-Adams is it's a way to take a basic LP relaxation and systematically strengthen it, trading off runtime for accuracy. So suppose that your initial basic LP has n variables. Then the level D Shirali-Adams linear program is a linear program in n to the d variables, which is also has a tighter approximation power. And once you get to exponential size linear programs or level n Shirali-Adams, you have a linear program that's equivalent to the integer program. Okay, so what De La Vega and Mathieu showed is that for each fixed integer d, there exists a sequence of graphs such that the Shirali-Adams value at level d on that graph is at most half plus epsilon. And then in 2009, Charikar-Makarichev strengthened the above result. So they showed that subexponential sized Shirali-Adams LP fail in the same way that polynomial sized Shirali-Adams LPs fail. They showed that for each epsilon, there exists some delta in a sequence of graphs growing with n, such that the level n to the delta Shirali-Adams relaxation has value at most half plus epsilon. Okay, so things aren't looking good for the Shirali-Adams LP. But a later sequence of works also showed that Shirali-Adams is not just any linear program, but in some sense it's the most powerful linear program. So in 2012, Chan, Lee, Raghavendra, and Stoyer showed that if any LP of size at most n to the d has ratio better than rho, so approximates better than rho, then a Shirali-Adams LP of comparable size, n to the 2d, does just as well. Okay, so if you're going to write down any linear program and you don't mind a quadratic difference in the size, you might as well write down the Shirali-Adams LP. So a lower bound against Shirali-Adams LPs of polynomial size automatically transfers to any LP of polynomial size, with the asterisk that the LP is not allowed to depend on the input graph. Okay, and then in 2017, Kothari, Mukta, and Raghavendra strengthened this result and showed that Shirali-Adams is the most powerful LP period. So this doesn't only apply to poly-size LPs, but it applies to linear programs of any size. And so the conclusion, combining this result of Charikar, Makarichev, and Kothari, Mecca, and Raghavendra, is that no linear program of sub-exponential size, of size less than 2 to the n to the 0.01, can approximate max cut better than 0.51. But then in 2019, Ryan O'Donnell and myself showed that you can actually get refutation using linear programs in pseudorandom graphs. So what does this mean? So suppose that our graph G satisfies the following pseudorandom condition. You require that the random walk matrix has all but the first eigenvalue bounded in magnitude by this number 1 over square root delta. Think of this as like 1 over polynomial in n. Then the level D Shirali-Adams LP, where D depends in this way upon delta, but don't try to absorb that for now, gets approximation ratio close to 1. Okay, so this condition is satisfied by, for example, a random delta regular graph with high probability. And if you plug in all of the parameters as necessary, you can get that, for example, in a Erdős-Rényi graph with average degree n to the 0.01, constant level Shirali-Adams achieves ratio 0.99999. Okay, so this is a very surprising result in the wake of the strong lower bounds that we've seen. But it's not clear whether this should apply to arbitrary graphs, right? Here we're requiring this, here we're requiring this pseudorandom condition. This pseudorandom condition actually automatically forces us not to have consider graphs that don't have a large max cut value. For example, so graphs with large max cut value have eigenvalues that are close to -1. For example, bipartite graphs have eigenvalues of equal to -1. Okay, so what we want to do is we want to extend this result to arbitrary graphs, which don't satisfy the pseudorandom condition. And what we want is we want to get approximation algorithms rather than refutation, since this condition restricts us to graphs that necessarily don't have very large objective values. Okay, and indeed in our work, that's exactly what we do. So we show that sub-exponential side linear programs can get non-trivial approximations to max cut in any graph. So this is a converse to the lower bound shown before. What we show is that there is an LP of size 2 to the n to the 0.01 that approximates max cut by at least half plus epsilon for some very tiny epsilon. Okay, so an LP of size 2 to the n to the 0.1 can't do better than 0.51, but it can do better than half. And we can then extend this to show that for many other combinatorial optimization problems, LPs do give non-trivial approximations, and they don't lag so far behind semidefinite programs. Okay, so in the very short amount of time that I've left, let me give a high-level proof overview. So in my prior work with Ryan, we show that you can solve the refutation problem in spectrally bounded graphs. So if all eigenvalues have magnitude at most epsilon, then some function of epsilon degree Shirali-Adams LP certifies that the max cut value is at most half plus epsilon prime. But we need to allow negative eigenvalues of magnitude close to 1 to accommodate graphs with large maximum cut. So that's to go from refutation to approximation. Okay, so the first step in our proof is to use ideas from the work of Ryan and myself from 2019 to get an algorithm that solves the rounding problem rather than the refutation problem in graphs that aren't spectrally bounded, but instead have low threshold rank. So what we show that if there's at most k eigenvalues bigger than tau, then some sufficiently high degree Shirali-Adams LP can be rounded to a cut of value equal to the max cut of the graph times 1 minus tau prime for some tau prime. Okay, so to explain how this works, let me first say what the degree D Shirali-Adams relaxation is very briefly. So degree D Shirali-Adams is the following. Say that I want to maximize some polynomial f of a degree at most d. Okay, so for example, you can think of f as encoding the fraction of edges cut in the graph. So what I do is I can feed that polynomial into the degree d Shirali-Adams LP relaxation. And what the LP relaxation gives me back is some function that goes from monomials of degree at most d in my variables to the reals. And the condition that this function will satisfy is that for any set of up to d variables, this function, which I'll call the Shirali-Adams pseudo-expectation, gives the marginals of a true probability distribution over strings of d plus or minus ones. Okay, so when I restrict to at most d variables, the pseudo expectation behaves like the true expectation of a variable. And this is entirely because of the fact that I'm working in a combinatorial setting. So I have, probability distribution over sets of up to d variables taking finitely many values. That means that I can represent all of my constraints as a linear program. So that's the kind of power of combinatorial optimization here. Okay, and the idea is to use something called a spider random walk to relate local correlations and global correlations, and then plug into the global correlation rounding framework of Baraka, Govender, and Stoyer. So the idea of Baraka, Govender, and Stoyer is the following. If I have a linear program where the covariances in this pseudo distribution along the edges are small, then independent rounding works well. And furthermore, there's a way to ensure that my average covariance globally is small. This is also part of the global correlation rounding framework of Baraka, Govender, and Stoyer. And what we do is we use the fact that random walks mix fast in graphs of bounded threshold rank in order to relate local and global correlations. So what we do is we do something called a spider random walk. So we choose a random variable, xi1, and then we do a length t random walk from that variable, and we repeat this process d minus 1 times to get a d minus 1 t spider. If I look at the if I look at a pair starting at the initial variable out to the endpoint of the walk, this is like a random walk of length t in the graph. And if I look at two distinct legs of the spider and I look at the kind of path between them, that's equivalent to a random walk of length 2t. This is just by properties of random walks. And now what I do is I use the fact that since I have at most d variables, if I look at the center and all of the legs of the spider, because my pseudo expectation operator is corresponding to an actual probability distribution, the covariance matrix must be positive semi-definite, and that gives some relationship between the value at length t random walks and the value at length 2t random walks. And in this way, starting with t being 1 and going up to t being n, I can relate local and global correlation as long as random walks mix fast. Okay, and then what we do is we partition the graph into pieces of low threshold rank, similar to what Aurora, Barak, Stoyer, and Stoyer do. So what we do is we take the graph and we remove pieces which contain a constant fraction of the edges. So every piece contains a constant fraction of the edges incident on it. And furthermore, each piece has low threshold rank. So we decompose the graph as follows. Within each such piece, we can get a good approximation using our algorithm here. And then for every edge not cut in this partition, we get value a half because we can use randomness. Okay, so in that way we get a half plus h of tau kappa approximation. So that's that. So allow me to conclude. So what we've shown is that sub-exponential size linear programs can get non-trivial approximations to max cut, unique games, and other 2 CSPs. Some interesting open questions are, can Shirali-Adams LPs give refined approximations? So for example, The Gomans-Williamson rounding of the semi-definite program approximates a graph of value 1 minus epsilon with factor 1 minus square root epsilon. Currently, this is outside of the reach of our techniques. The question is whether linear programs can do the same. Another question is, can linear programs certify expansion, or do linear programs of subexponential size have any proof similar to Cheeker's inequality for certifying expansion in graphs? Okay, thank you. Hope to see you at the real life talk at Fox.